Students, today we are going to see the new point from the radiation chemistry, and that point is the radiation dosimetry. So in the radiation dosimetry we are going to see few points, units of measuring radiation energy or the radiation dose. So here are the units: the rad, the gray, the Rontgen, RBE, REM, sievert. So these are the 6 units which are used for measuring the radiation energy or the radiation dose. Then we will see in today's lecture the Fricke dosimetry and the Ceric Sulphate dosimetry. So let's start with our today's lecture. So what is meant by radiation dosimetry? So dosimetry is the act of measuring or estimating radiation doses and assigning those doses to the individuals. So amount of energy that will be absorbed by the human body or any living thing or any object, and after that there is a certain reaction occurs and certain products will be formed. So the dosimetry is a simply act of measuring or estimating the amount of radiation doses. And here two types of the radiation exposures are there: external exposure and the internal exposure. So here is a difference between the external and the internal exposure is, in the external exposure, the radiation source or the nuclear substance which continuously emitting the alpha, beta, gamma radiations, that will be kept outside the body. And in the internal exposure, the nuclear substance or the radiation source which emits continuously alpha, beta, gamma radiations, that will be kept directly inside the body. So that is the difference. And here 3 methods which are commonly used to determine the radiation doses which was absorbed by the human beings. So first one is a personal dosimetry, then second one is airborne concentration measurement, and lastly the environmental pathways analysis. So we will see first the units for measuring the radiation energy. So as we know, in the radiochemistry or the nuclear chemistry, the units are much important, and we know the curie is unit for measuring the radioactivity. So 1 curie is equal to 3.7 into 10 raised to 10 disintegrations per second or becquerel. And becquerel is the SI unit of the radioactivity, and 1 becquerel is equal to 1 radioactive decay per second, which is equal to 2.703 into 10 raised to minus 11 curies. So this is the units, curie and the becquerel for measuring the radioactivity. But in the today's lecture we are studying the units for measuring the radiation energy or the radiation doses, and that units are here. So first unit is the rad. Here the correlation is given, or the definition of the rad is given: 1 rad. So the rad is shown by small r. So 1 rad is equal to absorption of 100 ergs energy per gram of the substance. So what is the relation? 1 rad is equal to 100 ergs per gram. So here is the equation given: R is equal to 10 raised to minus 5 joules per gram. So here the conversion is given: 1 rad is equal to 100 ergs per gram, and it is equivalent to 10 raised to minus 5 joules per gram. And when we convert that into the electron volts, the equation will be R is equal to 6.24 into 10 raised to plus 13 electron volts per gram. And here is a relation which I have written: 1 electron volt is equal to 1.602 into 10 raised to minus 19 joules. So just I have found the value of rad in the electron volt per gram. And if a target substance is liquid of density rho, as we know that any liquid material has a density and the density will be rho. So 1 rad is equal to 6.24 into 10 raised to 13 rho into electron volt per centimeter cube. Here the actual unit of rad is electron volt per gram, and when we are multiplying by density to the equation which we found here, the R value. So just here gram electron volt per gram is there and our density unit is gram per centimeter cube. So simply gram will get cancelled and the final unit of the liquid substance rad is electron volt per centimeter cube. So this is all about the rad. So 1 rad is equal to 100 ergs per gram, and that will be converted into joule. Then the value will be 10 raised to minus 5 joule per gram, and when we convert it into the electron volt per gram, the value is 6.24 into 10 raised to 13. And when the liquid substance is taken, we have to multiply the rad value by rho. So just I have multiplied the equation 6.24 into 10 raised to 13 by rho, and unit will be changed due to the density unit, that is gram per centimeter cube. Gram will get cancelled and the final unit is electron volt per centimeter cube. Now we will see the second unit, and here the 1 gray, and that will be notified as a GY. So 1 gray is equal to 1 joule per kg, and it is equal to 100 rads. So this gray, that unit is named after Dr. L.H. Gray, and it is necessary to include a unit for the rate of the energy absorption. So gray is the unit which is useful for the calculation of a rate of the energy absorption, and this is the dose rate, that is dose absorbed per second in units of rad per second or gray per second. So here the relation which is important, you have to keep in mind, 1 gray is equal to 1 joule per kg, which is equal to 100 rads. So this is the second unit. Now we will see the third unit, the Rontgen. So the Rontgen, and it is denoted by capital R. So the Rontgen is the unit of exposure dose, and based on the ability to the radiation to ionize the air. So here when the Rontgen unit is used, it is used for the exposure dose, and it is based on the ability of the radiations to ionize the air, and it is defined as the exposure to such dose that could produce in 1 centimeter cube of the dry air at STP, and here the ions carries 1 electrostatic unit of the electricity of either sign. So the Rontgen is a dose that could produce in the 1 centimeter cube dry air at the STP, and then there is ionization occur, and that ions will carry 1 electrostatic unit of the electricity of either sign. It will be positive and negative charges will be developed there due to ionization. So 1 rad, it is not rad, it is a Rontgen. So capital R is for the Rontgen and the small r for the rad. So here the capital R is here, that is 1 Rontgen. And we have seen here the air particles or the air will be ionized. So I have written here air. 1 Rontgen of air is equal to 0.87 rads, and this is equal to 8.7 milligrays. So this is the relation which you have to keep in your mind. 1 rad of air is nearly equal to 0.87 rad and it is equal to 8.7 milligrads. So we will see the fourth unit, that is RBE. Here the long form of the RBE is relative biological effectiveness. So biologists recognize the difference in the effectiveness of the different types of the radiations in their action on the live tissues, and they have graded them as RBE. So as we know, the alpha particle, beta particle and the gamma particle, or the radiations, alpha, beta, gamma radiations, X-ray radiations, when these radiations are bombarded on our body, then certain amount of the changes will be observed in the body. So when this alpha rays, gamma rays and the beta particle that will be came in contact with our body, some amount of the radiations will get absorbed into our body, and that will be calculated as a relative biological effectiveness. And RBE is equal to 1 for the X-rays, gamma rays and the beta particles. When our body will come into contact with the neutrons, the RBE value or the relative biological effectiveness, that value will be 2.5. And when the alpha particles or the fast neutrons or the protons, they came in our contact with our body, then the relative biological effectiveness value, that is RBE, should be 10. So RBE is 1 for the X-ray, gamma ray and the beta particles. Then for the thermal neutrons it is equal to 2.5, and for the alpha particle, fast neutron and the proton, the RBE will be 10. So simply the effectiveness of the different types of radiations in their action on live tissues, that will be different for X-rays, for thermal neutrons, for fast neutrons and the protons. Then we will see the next unit, that is the fifth unit is REM. You can write it as a capital R and small em. So this REM stands for Rontgen equivalent mammal or MAME. So simply when mammals will absorb the radiation doses, that will be calculated. So mostly mammals that can be considered as a human being. So REM, Rontgen equivalent mammal, is equal to RBE, that means relative biological effectiveness, into rads. So this is the equation of the REM. Here REM is related to the RBE and rads. So REM is just a product of the RBE and the rads. Then the last unit, and which is the SI unit of REM, this is a sievert. So 1 sievert, that is the SV, which is equal to relative biological effectiveness into grades. So as we have seen here, the second definition, 1 gray is equal to 1 joule per kg, which is equal to 100 rad. So simply rad is related to the gray. So here in this above equation, REM is related to rads. So instead of rads, we are writing here grades, because 1 rad is equal to 100 grades. Or here another equation is given, 1 sievert is equal to 100 REM. So simply 1 sievert is equal to RB into grades, and 1 sievert is equal to 100 REM. So all these 6 are the units of the measuring radiation energy and the radiation doses. So now we will see the Fricke dosimetry, and after that we will see the Ceric sulphate dosimetry. So here first one is a Fricke dosimeter. So Fricke dosimeter is a device which is used for measuring the dose. So most useful as a method to directly measure the numbers of reactive species in the solution. As we know, in the Fricke dosimetry there are the formation of the Fe2 plus ions and the Fe3 plus ions. then there are some free radicals will be formed like the OH radical, H radical and so on. So we will see this Fricke dosimeter in detail. So Fricke dosimetry, it measures the extent of oxidation of the Fe2 plus to Fe3 plus. So simply the oxidation of Fe will occur from Fe2 plus to Fe3 plus under specified conditions, and the Fricke solutions is obtained by dissolving 0.4 gram of the FeSO4 NH4 twice SO4 6 water molecules. So this is the compound which we have taken the 0.4, and then we have to dissolve this 0.4 weight of the FeSO4 NH4 twice SO4 6 water molecules, and then we have to add 0.06 gram of the sodium chloride in the 22 ml of the 95% to 98% H2SO4, and that solution will be diluted to 1 liter, and dissolved air is present in this solution. So what we have taken? Initially we have taken the 0.4 gram of the FeSO4 NH4 twice SO4 6 water molecules, and then we have added 0.06 gram of the sodium chloride in the 22 ml 95 to 98% pure H2SO4, and now we have to transfer this solution in the volumetric flask which is of a capacity 1 liter, and then we have to dilute with the water to the mark. So a sample of the solution in a thick enough container is exposed to the radiation at the desired spot for a definite period of time. So just take the sample solution in a thick enough container, and that solution is exposed to the radiation, and here we have to keep that solution for a definite period of time. Then immediately thereafter, the amount of Fe3 plus produced is determined spectrophotometrically at the wavelength of 304 nanometer. Means what? We have prepared solution 1 liter, then we have taken the sufficient amount of the sample in a thick container, and then this is exposed to the radiation, and then we have kept that sample there for certain period of time. Then immediately after that we have to measure the amount of Fe3 plus which is produced from the Fe2 plus, and that will be measured spectrophotometrically at a wavelength of the 304 nanometer. And at that time the molar absorptivity of the solution which is equal to 2174 per mole per centimeter. So this is the Fricke dosimetry, and here again we have measured the Fe3 plus amount on the spectrophotometry. So concentration of Fe3 plus produced is determined from an experimental plot of optical density against concentration. So on the y-axis there is optical density, and on the x-axis there is a concentration, and from that we have to determine the concentration of Fe3 plus ion. And the known dose is already calculated from the measured yield of Fe3 plus, knowing that the yield is 15.5 Fe3 plus ions per 100 electron volt dose absorbed. Because we have already provided a fixed dose, or the fixed amount of radiations will be provided to the substance, so the known dose is already calculated from the measured yield from the Fe3 plus, and knowing that the yield of the Fe3 plus is 15.5 ions per 100 electron volt dose absorbed. Means simply the yield of the Fe is 15.5 ions when we have provided the 100 electron volt dose, and that was absorbed by the Fe solution. So the method of the dosimetry that gives very reproducible values over a wide range of dose up to 0.5 kGy, that is a kilogram, or 50 kilo rads. So this is all about the Fricke dosimetry, which is related to oxidation of Fe2 to Fe3+. Now we will see the ceric sulphate dosimetry. So the ceric sulphate dosimeter, here a 1 to 10 millimolar solution of acidified ceric sulphate is exposed to the radiation. So initially we have to prepare 1 to 10 millimolar solution of the acidified ceric sulphate. Then we have to expose this solution to the radiation when cerium 2 plus is reduced to cerium 3 plus. So as in the Fricke dosimetry, Fe2 plus is oxidized to the Fe3 plus. Here the cerium 2 plus is reduced to cerium 3 plus. So it is not a cerium 2 plus, it is a cerium 4 plus. So cerium 4 plus is reduced to the cerium 3 plus, and the fall in the concentration of the cerium 4 plus is determined spectrophotometrically at 320 nanometer. So here is a cerium 4 plus. Keep in mind, this is a cerium 4 plus that is reduced to the cerium 3 plus. And when the cerium 4 plus is reducing to cerium 3 plus, the concentration will be decreasing. So fall in the concentration of the cerium 4 plus, that will be measured on the spectrophotometer, and the wavelength should be kept at a 320 nanometer. And the molar extinction coefficient for the 320 nanometer wavelength, that is 5565 per molar per centimeter. So molar absorption coefficient is 5565. When the cerium 4 plus concentration decreasing, that was measured at the 320 nanometer wavelength. Then the G value for the cerium 3 plus is a 2.44, and the ceric sulphate dosimeter is particularly useful for measuring the higher doses of the order of milligray, and which is equal to 10⁸ rads. So it is much sensitive in the presence of the organic impurities. So ceric sulphate dosimeter, here simply we have to measure the reduction of the C4 plus to the C3 plus, and measure the amount of concentration decreasing of the C4 plus at 320 nanometer wavelength on the spectrophotometry. Then the molar extinction coefficient should be 5565 per molar per centimeter, and the ceric sulphate dosimeter is mostly useful for the higher doses of the order of m gray, which is equal to 10⁸ rads, and the technique is more sensitive in the presence of the organic impurities. So students, what we have seen in the today's lecture, we have initially seen the 6 units of measuring the radiation doses or the radiation energy. After that we have seen the Fricke dosimetry, and now we have seen the ceric sulphate dosimeter use. So we will stop.